So welcome to the Homotopy Type Theory Electronic Seminar Talks. Today is especially exciting because we're expanding our list of time zones that we're covering. So we're still looking for someone from Tahiti, so if you know anyone who could speak to get a new time zone, let us know. But anyway, we're very happy to have Richard Garner from Macquarie University in Sydney, who will be telling us about polynomial comonads and comodules.
Thank you, Dan, and thanks very much for the invitation to speak. And thanks to all my European viewers who are, I think, an even more ungodly time than I am at the moment. So I'm going to be talking, as Dan said, about polynomial comonads and comodules. So I'm just going to start writing and let me know if there's any problems seeing this. Okay, so the title is Polynomial Comonads and comodules. Okay, so I guess the place to start here is to think about how would you describe an internal category in type theory? And really what this comes down to is how do you describe the relation between the objects and the arrows of an internal category? And really there are three ways of doing this. So three ways to think about internal categories in type theory. Okay, so I guess we always start with a type of objects. Let's call that C0. Okay, and I mean, I guess in practice you might want to restrict this so that it's, I don't know, like a one type or something like that. But for the moment, I'm just going to ignore those questions and we're just going to think about the basic structure that would underlie this. So we have a type of objects, but then for arrows, we've got three choices. Okay, so there's sort of the internal choice. I mean, we're talking about internal categories, but there's one that's sort of really internal. And so in this, I have another, another closed type of arrows C1. And then I just have two terms from the arrows to the objects, okay? All right, now there's also the version which is probably most familiar and that kind of comes most naturally, which I might call the enriched version. So in this, I have a dependent type of arrows that says given objects x and y in C0, I have a type C1 xy of arrows from x to y. Okay? All right, but then there's this other version, there's another version which is intermediate between the two, and I don't know, I don't have a good name for this, but what we could do is we have a dependent type of arrows, but rather than looking at all the arrows from x to y, I'm just going to have a dependent type of all arrows with domain x. And if I do that, then I have to record the target somehow. So what I have in addition is something which, given an object x and an arrow f with domain x, returns a target in C0. Okay? All right, so we have these three choices. Now, I don't know if any of you have ever tried using choice 3, but it's important in various places. So if you look at in algebraic geometry or in differential geometry, then, or in operator algebra, then people are interested in étale groupoids. So étale groupoids are groupoids whose source map is a local homeomorphism. And there you have this this aspect to it that somehow the source map is treated differently from the target map. And if it's a groupoid, actually it doesn't make any difference because the source and the target maps are kind of plays similar roles. But if I've got a genuine category, then I can ask that the source map be a local homeomorphism, and that's something that sort of has some importance. Okay, and so what I want to do today is to understand this third point of view better. And it turns out that it comes out of quite an interesting bunch of structure, which I think deserves to be better known than it is. Okay. So that's the sort of preliminary. So here's what I'm actually going to tell you about. So the first section is going to be about the multi-category poly-E. Okay, so I gave you a type theoretic gloss, but this is mainly going to be just kind of category theory, but I'll explain the type theoretic interpretation of it as I go along. So what we're going to do is we're just going to start with a category E with a class of display maps D. Okay, so I mean, as far as I'm concerned, all that means is I've got a class of maps D, which admit all pullbacks, and which I'm going to think of as dependent projections in some type theory, perhaps. Okay, so from this, I can define a category poly-E with, so an object is just a D map, which I'm going to write as P from E to B. Okay, and so that is, if you like, saying that for B in B, I have some family of types E of B. Okay? All right, so what are the morphisms in this category? And this is where things get a bit interesting. So there's an obvious notion of morphism you might have between these D maps, which essentially amounts to a commuting square. That's not the morphism I want to look at. So I'm going to say that a map from P to P, sorry, from P to P prime looks like this. So I've got E down to B here, and I've got E primed down to B here, and a map from EB to E prime down to B primed is a map F from B prime to B. Then I take a pullback, and then I give a map G from that pullback into E primed. Okay, so if I write that down, what am I actually doing? I'm saying that given B in B primed, or let's say B primed in B primed, I give F of B primed in B. And then given B primed in B primed, and given E in E of F of B primed, I'm going to give G B primed E, and that's in, I've done it again, let me move this over a bit. That is in, what's it in? It's in E primed of B primed. Okay. All right, so that gives you a nice category where the composition is as follows. So composite of this map, above map, with another map H, K from P prime to P double primed. Well, let me draw the picture and then write down the what that comes out to in terms of in elements. So here I've got E down to B. Okay, so I've got B primed here, and I've got my map F along the bottom, and I take a pullback here. Okay, and then I have my map G, which goes like this into E primed here. Okay, is that clear? That's just the first map. Right, now the second map is, I've got my H here coming from B primed. I'll explain what's going on in a moment, but let me just finish this and then we can try and understand what the hell it means. So I can pull back all this stuff here and I get something like this. Okay, and maybe let's do this a bit better here. Okay, so that map there was G, and that means this map here I could reasonably call H upper star of G. All right, and then the second part of my map from P prime to P double prime is this map K here going into E double prime there. And so now you can see, if I paste together all these pullbacks I have in this diagram, to pull back the map P on the left along F and H, when I do that, I get, what do I get? I guess I get this big composite here on the right. So down the right here, this object at the top right maps down to B double prime, and that is just the pullback of P along FH. Okay, and so then the comparison map from there into E double prime gives me the second component of the composite. So I can say that composite is it's going to be a pair which is FH and then K composed with H upper star of G. Okay, phew. All right, so, and then if I write that out in the notation, just in elements, what do I have? I see, well, I've got my F and my H, and I just compose those together. So the composite here takes an element B double primed in B double primed, and it returns F of H of B double primed in B. And then for the second component, I need to take a B double primed in B double primed together with an E in E of FH B double primed. And from that, I'm going to produce an element in E double primed of B double primed, and that element I can write as K of B double primed, comma, G of H B double primed, E. Okay, so what is this category I've just written down? Well, there are various ways of thinking about it. One is as follows. So my display maps constitute a fibration over my base category E. Whenever I've got a fibration, I can just take the opposites in each fiber and stick those back together and get a new fibration. And if I do that to the fibration of D maps, I get this fibration here, which is the opposite fibration of the fibration of D maps. So if I was in a locally Cartesian closed category, then I have the notion of a polynomial. I won't go into what a polynomial in detail is, but there's a bicategory of polynomials, and this is one of the Hom categories of that bicategory. In fact, it's the Hom category of polynomials from 1 to 1 in a locally Cartesian closed category. Okay. All right. But maybe a fun way of thinking about this, which I want to also spell out, is one that I guess was taken up by Peter Hancock and Anton Setzer, which is a view of, well, the idea is you view a D map as something like a very simple kind of game or interaction system. So the idea is I view an element in, so suppose I got a D map P from E to B, okay? So I've got my base type B, and I think of elements in my base type B as being something like commands, and I think of elements in E of B as being responses to that command, okay? So your command might be request an integer from the user, and then the possible responses would be all integers or something like that. Okay? Or if you prefer a slightly more abstract view, you could say this is some very simple kind of game. Okay, so the game is as follows. Opponent chooses a move from B, and then player gives a response in E of B. Okay? All right, and if you take that view, then I can talk about strategies for this game. So an opponent strategy for this game is just to choose an opening move, which is an element of B. And a player strategy for this game says, whichever opening move opponent chooses, I provide a response, which is an element of E of B. And so that amounts to giving a section of this D map. Okay? So maybe I should write a few words about that. So idea. I mean, there are lots of ideas, right? But this is one idea. So P from E to B is a game. So opponent chooses some B in B, and player chooses a response in E of B. Okay, and then the game's over. It's a slightly dull game, but there you go. I mean, it seems dull, but it's actually enough to get quite far. So, all right, and so then a opponent strategy is a choice of B in B, and a player strategy is a section of P. Okay? All right, and then so in terms of this, you can understand what these maps are. So a map from P to P primed in poly of E well, basically what it does is it allows player strategies for the game P to the left. Let me up here. So if I look again at what a map from P to P primed is, I can imagine having a player strategy for the game P on the left and an opponent strategy for the game P primed on the right. And what a map from P to P prime does is allows me to play those strategies in these different games against each other. Okay? So opponent playing according to his strategy chooses an element in B primed. So my map from P to P primed takes that opening move in P primed and transforms it to an opening move in P via F. Now in the game P, the player strategy chooses a response, which is an element in E over F of B. Okay, so an element in EF, sorry, let's say I started with B primed as we have here. So I start with B primed, the opening move in P primed. That produces an opening move FB primed in B. The player strategy produces an element in E of FB primed. And then, well, the second part of this map from P to P primed produces from that a response to the original opening move over in P primed. Okay, does that make sense? Is there any questions about that? Okay, good. All right, so a map from P to P primed allows a O strategy for P primed to be played against a P strategy for P. Okay, and so I guess a word you might use for that is a simulation. So you could say that it allows the game P to simulate the game P primed. Okay, and you can see there's some choice here. I mean, you could ask your maps to go the other way around. I mean, there's no particularly canonical choice here, right? So, I mean, the F and G point in different directions. So you could ask that, you could consider this a map from P prime to P, but I mean, it doesn't make much difference. Okay, so we've got this category. Now, in fact, this isn't just a category. I can make it into a multi-category. Okay, so are people familiar with what a multi-category is? Is there anyone who'd like to shake their head vigorously if they're not? Okay, I can see one vigorous shaking of a head there. Okay, so the idea of a multi-category is as follows. So in a category, I have objects and I have morphisms, and each morphism has a domain and a codomain. In a multi-category, I have objects and I have morphisms, but my morphism has a single codomain, but it has a list of objects as its domain. So you might think abelian groups is a category because it's got morphisms which are linear maps. But I can enhance it to a multi-category where in the multi-category, the maps with codomain n and domain M1, M2, M3, M4 are quadrilinear maps from M1 times M2 times M3 times M4 into N. Okay? So that's the idea. I have a notion of maps where there are possibly many inputs to my map and just a single output. And just as in a category, there are axioms about units and associativity and things like this. Okay, but the key thing to bear in mind is in a multi-category, my maps can have many inputs and one output. So let me describe how I can do that with poly E. So poly E can be made into a multi-category. Okay, so the objects as before. So the unary maps, the maps with a single input. So that's P to P primed. I'm going to put a brackets around the P because this is going to be a list in general, and this is a singleton list. And these are just going to be the same things I wrote down before. Let me tell you about the nullary maps. So a nullary map has no source input, and it has just a single thing as output. So this is a D map, and a nullary map are just sections of P prime. Okay? All right, so we'll see why that's true in a minute. Or, well, I'm just telling you, but we'll see why it's reasonable in a minute. So then the fun part is what the n-ary maps from, say, P1 up to Pn to P primed for n greater than 2 are. And I'm just going to draw you a picture. Okay. All right, so how's this going to work? So over here on the left, I'm going to write down, I'm just going to array here P1 up to Pn down the left. Okay, they're not joined together, they're just sitting above each other. So here's P1, P2 up to Pn. And over on the right here, I'm going to put P prime. Okay, so what's the data for this map? Well, the first datum is a map across the bottom here, which I'm going to call F1. Okay, so remember before, once I got my F1, I then took the pullback against what was then P and is now P1. So I'm going to do that. So there's my pullback. Okay, nice pullback. Okay, so now previously I mapped from that pullback into the domain of P primed. This time I've got a bunch more maps, so I'm just going to keep going to the left. So the next thing I provide is a map F2, like this. Okay, then I'm going to take another pullback. That gives me another map here. Okay, and I'm going to carry on like this. And eventually, I produce a map Fn here. I'll pull that back. I've got an object here. And here I've got a big string of composable arrows down into the codomain of P prime. And then the final datum I give is a G, which goes there and makes that little square commute. Okay. All right, so that looks a bit kind of weird, maybe. And you can sit here and you can write down what this is in the type theoretic nomenclature, which I'm not going to do. But I'm going to explain what the idea is. Okay. So, I mean, and I'm not going to tell you what the composition of these things is, but it's sort of a generalization of what I wrote down before, but I'll tell you what the idea is. So the idea is that an n-ary map allows strategies, let's say, allows an O strategy for P primed to be played against P strategies for each of P1 up to Pn. Okay? So let's see how this works. Okay, so an opponent strategy for P primed is just choose an opening move. Okay? And a P strategy for each of the games P1 up to Pn is a section which says choose a response to each opening move. So we can just trace through what happens. So suppose I've got an opponent strategy for P primed. So I have an opening move in P primed. Okay, well, I can use F1 to copy that to an opening move in P1. I can use the strategy I have for P1 to choose a response. That response, together with the opening move I had to begin with, gives me an element in this pullback. And I can use F2 on that to produce an opening move in P2. The strategy for P2 then produces a response to that, which in turn induces an element of this next pullback. And then I can apply F3 to that and carry on. Eventually I get up to the point where I use Fn to produce an opening move in the game Pn. Finally, my strategy for Pn produces a response to that. That produces an element in this top pullback here. And then I can use G, finally, to produce a response to the original opening move in the game P prime. All right? So that's kind of, I mean, that makes it clear where these morphisms come from. Okay, and I should say that really this is due to Mark Webber. So this is all due to Mark Webber in a paper called something like Polynomials in a Category with Pullbacks. Okay. And I should say when D maps are exponentiable, so pullback along them has a right adjoint, this multi-category is actually a monoidal category. So if I've got a multi-category, it could be that the n-ary multi-maps are represented by maps out of some tensor product of all the things in the domain. And in this case, with tensor being polynomial composition. So if you don't know what that is, then it doesn't really matter. And if you do, then now you know why I've written down this multi-category. Okay? All right. So we've got this multi-category. All right, now multi-categories are some kind of generalization of monoidal categories. Indeed, every monoidal category gives you a multi-category where the n-ary multi-maps from A1 up to AN into B are just mapped from A1 tensor A2 tensor AN into B. Okay? And so just as you can talk about monoids in a monoidal category, you can also talk about monoids in a multi-category. So in any multi-category M, a monoid is an object X together with multi-maps. So a nullary multi-map from nothing into X and a binary multi-map from X into X plus axioms. Okay? So we can ask, what's a monoid in poly of E? Well, we can just start writing it down, right? So we know that it's these data are up here. So first of all, it's an object. And what are objects? Well, they're D maps. Let's call it C1, C0. And I'm going to call this map S, rather suggestively. And yes, I'm going to think of this as X in C0, C1 of X. Okay. So what next? Well, we've got this nullary map from nothing into S. And that, remember, a nullary map is just a section of this D map. So it's a section I of S. And if you write out what that says, it says that given X in C0, I'm going to give something called I of X, and that's going to be in C1 of X. Okay? All right, now remember what I started by telling you, which is that there are various ways of thinking about categories in type theory. And you'll notice the first line I wrote down is my mysterious third way of talking about categories. That was how we described the set of objects and the set of arrows, C1x being the arrows out of X. And this, you will notice now, looks a bit like what you might expect for the identities operation in such a category, namely given an object, I can produce an arrow IX with domain X. Okay, so far we've said nothing about the codomain of this arrow, but that's okay. We don't have to do everything at once. We haven't finished describing what a monoid is. Okay, so then we have a binary map. This is the final datum from S into S. Okay, and what does this look like? Well, it looks like one of these funny pictures that I drew above, but just in the binary case. So let me draw that for you. I've got C1 down to C0, C1 down to C0. That's 2 copies of S on the left, and then on the right here, I've got just 1 copy of that. Okay, so the first datum is a map across the bottom from C0 to C0. Now, I'm going to cheat a bit here. Looking ahead, I know that this map has to interact nicely with the nullary map, I. I'm going to call this binary map M. Okay, and looking ahead, part of that, the axiomatics will force this map to be the identity. So I'm just going to assume that already at this point. So if that maps the identity, when I take this pullback, I just get S again. 1. Okay, so this is forced by unit axiom. Okay, so the first map is this map 1 across the bottom. Maybe I'll draw the things I have to actually give in blue or something. Okay, so there's the 1, I have to give that, and it's forced to be 1. So the second thing I have to give is, oh dear, is a map here from the pullback into this object here. And this I'm going to suggestively call T. And then finally, I take a pullback here. And the object I get here is C1 times over TS C1. And I have to give a map from there back into C1, which I'm going to call M. All right, and if I look at what these data actually are, then what do I have? I have given x in C0 and f in C1 of x, I have to give t x f in C0. Okay, so that's what the map T is in this lingo. And on the other hand, if I work out what the map M is, it says given x in C0 and f in C1 of x, so that's an arrow with domain x, and then an arrow G, and what does G have? It has domain, the target of f. And given given x, f, g, I'm going to produce m, x, f, g, and that's an arrow in C1 of x. So that should again have domain x, right? Okay. So the typing of that last one is the commutativity of this right-hand square. All right. So that you will observe looks just like the data of a category. Okay. So we have the data of a category expressed in style of 3. Okay, so remember 3 was this thing I didn't have a name for. And okay, so then, and the monoid axioms. So remember, I'm describing a monoid in this multi-category of polynomials, and I've just described the data there, and then there's some axioms. And the monoid axioms express exactly what you would think the category axioms should be. And given the data I've written down, I'm sure you would have no problem writing down the correct category axioms, and these should hold strictly. I mean, everything here is strict because this is just an ordinary category at the moment. And it's a multi-category, but it's an ordinary multi-category. It's not higher dimensional in any way. And so if you write down the category axiom up to definitional equality, then you'll have written down exactly the axioms that have to be satisfied here. Okay. All right. So this is, I think I'm going to attribute this observation to Ahman and Uustalu. I've forgotten the name of the paper. I'll have to get back to you. I think it's something like "What is a lens really?" or something like that. I think there are 2 papers by Ahman and Uustalu. So if you look at both of those, then you'll find it in there somewhere. So they're talking about containers, which is another name for polynomials, and they make this observation that this structure here, a monoid in this multi-category, is also describable as a polynomial comonad. Okay, so why is that? Well, it's because I've written my arrows in a particular direction, and if you wrote them in the other direction, then all the things that are monoids become comonoids, and a comonad is a kind of comonoid. So there you go. So now, Ahman and Uustalu observed this fact. Okay, and then there's a warning. And I mean, it's not just a warning, it's actually something that's quite interesting, I think. So I said that these monoids are just categories. So then you can ask, what are the monoid morphisms between them? And I mean, you probably do what everyone does and just sort of go, oh, well, they must be the functors, right? And you would be wrong if you made that assumption. So the monoid, okay, so if C and D are internal categories, seen as monoids in poly E. Okay. Then monoid maps between them. So we're in a multi-category. So what's a monoid map between two monoids in a multi-category? Well, it's just a unary map between the underlying objects which interact in the expected way with the unit and the multiplication. Okay. All right. Now I can work out what this is. Well, a monoid map between them involves something that looks like this, right? I've got C1 down to C0, and D1 down to D0, and here's my source map. Okay. Well, it involves an F0 going from D0 to C0. I mean, it doesn't look terrible so far. That's normally the data for a functor. But then something awful happens, which is that on morphisms, I appear to have to give a map F1 that goes in the other direction. Okay, so that looks weird, but it's a thing. So there's a different notion of morphism between categories called a cofunctor. These are, in fact, cofunctors. Okay, so you might think this is a problem and that you've never heard of a cofunctor and that therefore there must be something suspect about this. But it turns out cofunctors are really useful and play an important role in all kinds of unexpected areas of mathematics, and more people should know about them. So you can find them in a paper of Higgins and Mackenzie. So they introduced them in the context of Lie groupoids. So they're interested in the functoriality of the process taking a Lie groupoid to its Lie algebroid. And that's not functorial with respect to just ordinary functors, but it is with respect to cofunctors. Similarly, if I take a topological groupoid, I can associate to it a convolution algebra. And again, that's not functorial with respect to functors, but it is with respect to these cofunctors. So Higgins and Mackenzie have this, but the place I would suggest looking is in Marcelo Aguiar's PhD thesis, which has a substantial amount of stuff about cofunctors in it. Okay, so I don't want to say too much about cofunctors, but just to point out that they're important and that they turn up in this context where you maybe wouldn't expect to see them.
Richard, can I guess what a cofunctor is? I mean, if this is right or not. So as you indicated, it's a mapping on the objects from the objects of D0 to C0. And then if you were writing down the data of a category from like the enriched point of view, so that part of the action of a functor would be a map from a Hom set or a Hom object to a Hom type to a Hom type. Is a cofunctor thing you get by just turning that arrow around and then keeping all the commutative diagrams otherwise?
Yeah, that's right. So I mean, kind of the picture. So a picture I could draw is something like this. So I've got C0, C0, and I could think I've got C1 like this. Then I've got D0, D0, D1. Okay, so I mean, maybe I should swap the C's and D's around. Why don't I do that? Okay, so let's put the D at the top. D1, D0, D0, and at the bottom I've got C0, C1, C0. So here's F0 here, F0, and then F1 looks like that. So a normal functor would have the F1 pointing down, and then the cofunctor, I have the F1 pointing up. Okay, so I mean, if I think this is a double category, that doesn't really make sense, but if I think that I can use whatever they're called, companions and conjoints, to turn these F0s into these horizontal arrows, then I can make sense of a diagram like this. And I think this is what Bob Perret talked about this year at the CT conference. yeah, so that's what a cofunctor is. So another way of saying what a cofunctor from C to D is that it's a span where one leg is a bijective on objects functor and the other leg is a discrete, I want to say here, a discrete opt fibration. Okay, so there are all these different views on cofunctors, and I think they're very interesting. But what I want to talk about in the last quarter of an hour is something which I found quite surprising. So somehow, after a while, when you sit and stare at this, then kind of you get used to this perspective, and the fact that these things are internal categories is maybe no longer surprising. But this bit I have really no explanation for. So we've seen that monoids in this multi-category are internal categories. I mean, okay, if I'm being more precise, they're internal categories in E whose source projection is a display map. Okay, so that's more precisely what they are. And that ties in with the things I said at the start. So I mean, I could look at E being topological spaces, and then my class of maps D could be the local homeomorphisms, and then the monoids in this multi-category would be the source étale topological categories, the ones whose source map was a local homeomorphism. All right, but the thing that's really surprising, I think, to me is, well, what's a bimodule in here? So first of all, let's say what I mean by a bimodule in a multi-category. So bimodule in a multi-category M, well, it's something that goes between monoids, X and Y is, and basically you just copy the usual definition of a bimodule between, I don't know, between rings, say. So it's an object M, and then I have multi-maps from XM into M, which I'll call lambda, and then I have one from MY into M, which I'll call rho. So you think of those as a left and a right action plus axioms. Okay, and what do the axioms say? Well, there's something about lambda being a left action, which means compatibility with the mu and the eta for X, and then rho is a right action, which involves compatibility with the mu and the eta for Y. And then there's a bimodule condition, which says that if I start in X, M, Y, and then do lambda and rho in either order, I always end up in the same place. I get the same map into M. Okay? All right, so I can just write down, I can write this down in any multi-category, and it reduces to familiar notions in many familiar cases. So I can ask, what is a bimodule? In poly E between internal categories C and D. Okay, so reasonable question. And I had no idea what the answer would be before I started doing it. I'm not going to go through all the details because they're kind of a bit hairy, but I'm going to at least show you the pictures and then tell you what the answer is. So first of all, I have an object, and an object is a D map, E to B, a D map. All right, so again, that's something that says, well, for X in B, I have EX, a type. Okay, and then I have to give this left action and this right action. And you kind of have to have a bit of faith here, because you start and it looks terrible and you've got no idea what's going on. And I'm going to draw I'll draw the diagrams. I won't give you the type theoretic gloss on this, but I'll just draw the diagrams and then tell you what that amounts to. I've drawn the wrong diagram. Okay, good. So E and B. So E has an action by C. So here's C. So there's the source map of C, and then I've got this given map pi like this. Okay, and then the picture I have to draw is this one that I've drawn a few times now, so I'll draw it slightly quicker. So I have this and this, and I'll take a pullback here, and I have a map here, and I have to give here three pieces of data. And so what's that? There's the map across the bottom here, which I'm going to call P. The next thing I give is this map from the pullback into B, which I call alpha, and then there's this third map across the top, which is beta. Okay, and there are heaps of conditions which after some effort you discover turns out to be the same as giving, so I've got my category C down here. So if I look at the data, I've got B, which sits over the objects of C0, and then I pull that back along the source map and I give another map back into B. Okay? And that is the way that in internal category theory, you talk about a covariant presheaf on C, which can also be expressed as a discrete op fibration. So this is a discrete op fibration. Okay, so then there's some other datum here, which is this map beta, which might look a bit mysterious, and I'm not going to try and justify this, but it turns out that this, in turn, amounts to giving a further discrete fibration over B. Okay, so B here is, so this category bold-faced B on the right has as its set of objects B, and as its set of morphisms, the domain of this pullback of P along S. Okay, and then E here has as its set of objects E, and then I guess its morphisms must be given by some corresponding pullback, which I'm not going to try and write down. Okay, so you just do this, and it turns out to be this. And okay, it seems a bit weird, but oh well. So how about a right action by D involves a D1, D0, so here's D, and then there's an E and a B here this time. Okay, so you'll note that the D's at the top here, whereas C was at the bottom before, and that's because one was a right action and the other was a left action. And on the right here, I've got pi. All right, so again, there are these maps. So let's draw them in. And again, there should be three maps, but one of them again turns out to be forced to be the identity. So that's good. And in fact, that tells me that this object here must also be E, and that map there must also be pi. So now I have to give a map here, which I'm going to call Q, and I have to give a map at the top, which I'm going to call gamma. And again, I'm not going to go through this, but this turns out to be the same as something like this. So I've got E sitting over D via a map Q, and then I've got this map pi, and this is going into a discrete category on B. Okay, and the condition is that Q is fibre-wise a discrete fibration. So what does fibre-wise mean? It means the fibres over B on the right here. So I can look at each I can restrict this Q back to each of the individual fibers of B, and on each of those fibers, it's a discrete fibration. Okay? All right. Again, looks weird. But what we haven't yet done is look at the bimodule condition, and this forces some compatibility. And so in the end, what you get, rather amazingly, is this. I've got D here, I've got an E here, and then I have B here, and I have C here. So I have a diagram of maps like this in the shape of what some of you may recognize as the shape of a polynomial, a more general polynomial that I referred to earlier. And there's some maps here, Q, pi, and P, and there are some conditions. And the conditions are that P is a discrete op fibration, and that Q pi is what's known as a two-sided discrete fibration. Okay. So I said discrete op fibration is the way you talk about covariant presheaves on an internal category. So in this case, that's a covariant presheaf on the internal category C. So a two-sided discrete fibration is the way you talk about a profunctor between two internal categories. So this here is a profunctor between the internal categories D and B. Okay, and also note that there's some conditions I haven't really been too explicit about, but some of these maps are forced to be D maps. In particular, the map pi here in the middle thing is a D map. So the map from E down to B, whereas these maps P and Q are not actually involving D maps. So there's a finer analysis shows that there's some sort of slight difference in the treatment of these various legs of this diagram. Okay, well, I don't know. I mean, some of you may look at this and think this looked great already, but maybe what I should just conclude by telling you, I think I can probably, if I can take another 5 minutes, maybe, is that okay? Is just that these are a very, very natural class of functor which turn up throughout kind of combinatorial category theory. So I'll just sort of very briefly tell you about how these correspond to these so-called parametric right adjoint functors. Okay, so what is a parametric right adjoint functor? Well, suppose that E and F are categories with terminal objects. Then a functor, F from E to curly F, is parametric right adjoint. Some people say local right adjoint. If, well, each object of E has a map down to the terminal object. So when I hit that with F, each object in the image has a map down to F of 1. And so I'm going to ask that this has a left adjoint, or is a right adjoint. Okay, so right adjoint functor is one that preserves all limits, plus some other stuff maybe, but in general it's a functor that preserves all limits. I mean, in particular it's a functor that preserves all limits. So a parametric right adjoint you can think of as one that preserves not all limits, but all connected limits, all ones that aren't the terminal object basically. Okay. All right, and so what I just want to finish by explaining to you is how diagrams like star actually correspond to parametric right adjoint functors between presheaf categories. So again, this analysis is, I think, maybe due to, I mean, it's not a very difficult analysis to make, but I think it's spelt out by Mark Webber in one of his papers on this topic. I can't exactly remember which one, but let's repeat it here. So suppose I've got small categories C and D. I can ask, what are parametric right adjoint functors from pre-sheaves on D, covariant pre-sheaves on D, to covariant pre-sheaves on C? Well, they're the same as right adjoints from D set into C set sliced over whatever my functor sends the terminal object to. Okay, so for some x in C comma set. Okay, if we've got a parametric right adjoint, then by definition I can put f of 1 here for the x, and conversely, if I've got a functor of this form, then I can compose with a forgetful functor down to C comma set, and that gives me a parametric right adjoint, and those two processes are inverse to each other. All right, well, those are the same as left adjoint from C set on X into D set. Okay, well, a left adjoint out of C set on X, C set on X is itself a pre-sheaf category, right? It's the category of covariant pre-sheaves on the category of elements of X. And a left adjoint functor out of a pre-sheaf category is the same as just any old functor out of the category on which it is pre-sheaves. Okay, so these are the same just as mere functors from the category of elements of X op into D comma set. All right, now that there, what I've written down, that's the same as a profunctor or a bimodule from the category of elements of X to D. And from what I said earlier, those are the same as two-sided discrete fibrations from D to the category of elements of X. And so let's call this thing in the middle E. Why not? Okay. All right, but what's the category of elements of X? That's simply the domain of the discrete op fibration corresponding to the pre-sheaf X. So that's just the same as giving a diagram like this, D, E, B, so B is now Lx, and then down to C, where this is a discrete op fibration. So every discrete op fibration is of the form category of elements of a pre-sheaf down into C. Okay, and then this here is a two-sided discrete fibration. Okay, so we get this sort of amazing fact. So i.e., bimodules from C to D in this bicategory of polynomials are the same as parametric right adjoint functors well, okay, let's be precise, in poly set. So if I just do this in set, then I literally get that these bimodules are the same as parametric right adjoint functors from D comma set into C comma set. And so in general, I guess this is a way of producing a notion of parametric right adjoint functor for internal categories in whatever context you feel like. Now, an obvious question is, and I'll just say some words, but I won't write anything about this, is, well, I can compose parametric right adjoint functors between pre-sheaf categories. It's easy to see that the notion is stable under composition. And so you can reasonably ask if that's true in general. If I look at these bimodules in poly E for some other E, then do I get a nice category of these things or something like that? And well, I guess the answer is in general, no. If I look at the bimodules in a multi-category, I don't necessarily get a nice category of these things. There's not necessarily a way of composing them, but they do always form a so-called virtual double category. And under good conditions, that virtual double category will, its multi-maps will admit representations, and then we do get, in fact, a bicategory out of this. And I think this will be true so long as all your maps, all your display maps are exponentiable, which is what we needed for the original multi-category to be representable by something. And some other condition, which is something to do with kind of, I don't know, co-reflexive equalizers of certain kinds of diagrams that are preserved by pullback or something like that. So I haven't quite worked this out, but I think just by applying general principles, you can figure out what you need to describe the composition of these things, which is kind of fun because in the set case, it's a little bit complicated to write down the formulae. All right, and I think that would be an excellent place to stop. Thanks for your patience as I sort of spilled over a few minutes, and I'll stop there. So thank you all.
Okay, thank you very much, Richard. So as is our custom these days, we will applaud silently, visually. Okay, so now we have time for questions. Does anyone have a question? Just unmute your mic if you do.
I have a question. So there's another viewpoint on this category of polynomials that you described, which I don't think you mentioned, which is that it's a dialectica construction.
Right. Right.
So maybe if I have to come up with an actual question about that. So, but one thing that I've been wondering is whether there's any chance that your multi-category, the maps seem to be kind of going the other way. So I was wondering if there's any chance that this multi-category is actually a polycategory or something like that.
I mean, so there are obvious questions which are about, I gave this view in terms of games, which I guess is closely related to this dialectica business. And so that there is a question of, suppose I just wanted not just these games with a move and a response, but maybe I carry on playing for a while. And then is there some corresponding structure that goes on that you get from this? And what does it look like and how does it work? And I don't know. I'm not sure if that's the sort of thing that maybe you were thinking of, or...
Well, okay, could you scroll back up to where you were talking about the multi-category and the games?
Yeah, sure.
So you said, sorry, down here.
Yeah.
An n-ary map allows an O strategy for P prime to be played against P strategies for each of P1 through Pn. But obviously, it seems obvious to me you would like, well, couldn't we have O strategies for more than one game, as well as P strategies for more than one game, and allow them to be played against each other?
Right. I think a prerequisite for that would be the thing I mentioned, because I don't know. It seems like if an O strategy is just a single move, oh no, maybe that's not a problem. Maybe you're right. Maybe there is some way that you could set up some kind of polycategory with these things. Okay. So maybe here's the thing. So this is all part of this kind of game semantics picture for linear logic. But there, rather than having maps like F1, F2, Fn, and G, you'd have relations rather. And I think if you had relations, then I would guess, yes, you can get a polycategory out of this. And I guess those correspond to a slightly weaker notion of simulation than if these things are really, really functions. And I think that would probably be I'm feeling my way towards an answer here, but I feel like that's probably the setting in which you could sensibly construct a polycategory out of these things. And in a sense, once you restrict to the functions, then, I mean, you're choosing a kind of direction of proof kind of thing, and then you can't get the things you need for the polycategory out of it. I mean, I don't know if that's true or not, but that's just my feeling.
Okay, any more questions? I'll ask Richard. Can you say more? Did you have any assumptions on the set of display maps that you started with?
I think all I needed is that they're closed under pullback, more or less. I mean, that's enough to define this multi-category.
Mm-hmm.
If they're exponential, then I get an actual monoidal category, as well, that seems to be written on the screen right there. But yeah, I mean, you don't need anything beyond that, I think. I think it all works out. So I mean, that's the point of Mark's paper, more or less, is that if I've got enough pullbacks, then I don't need that much more to talk about polynomials.
Mm-hmm. Okay.
So I mean, an interesting question, I think, is I haven't really thought about this, but okay, so I mean, suppose you really wanted to do this in type theory, then well, normally you'd use this sort of enriched perspective, and you'd have a type of object and Hom types between every pair of objects, and then you might reasonably assume that say the objects were a one type and all your Hom types were zero types, and then you might add some extra stuff onto that. But in any case, that's a context in which all the strictness I've got here kind of continues to work in an intentional setting. So then the question is, suppose I do this one-sided version and I just make those same assumptions. So I've got a one type of object and then the collection of all morphisms out of an object is a zero type. Now, is that sensible? I don't know, but it sort of seems interesting to try and see if kinds of internal category you get in practice would have this property or not.
Yeah, it feels like the set of morphisms where only one object is fixed should be a one type as well, because it's acted on by the automorphisms.
Yes, that's right. Yes, I haven't thought about this at all, actually, but I suspect that could be the case. And in which case, is there any sensible axiomatics you could use to turn these equalities into some kind of intentional equalities that would still make this notion make sense, or is it just as doomed as the kind of completely internal version?
Okay, more questions? Last chance. There's got to be a couple more. Okay, well, if not, we will thank Richard again.
And thank you all for being an attentive audience.
Okay, and that's it for this semester. We resume January 23rd, and the lineup of our talks for the next semester are all on the Hottest website, so you can look there. Okay, see you later.